I think there has never been as careful a selection over so many years of speaker for a symposium, and I have no doubt that we are going to learn a great deal from all. Our first speaker is Professor Arthur Adamson of the University of Southern California, who received the Kendall Award in '79, and his topic at the time was the solid vapor and the related solid-liquid interface. This time, he is going to talk to us about the adsorbed state in vapor adsorption and in solution adsorption. Professor Adamson is a very remarkable man, as you know, but I don't know whether you realize that he is either the only or at least one of the very few people who have received 3 ACS awards in different fields. He has received the Kendall Award, the award in chemical education, as well as the one in inorganic chemistry. Arthur, it's all yours.
Is this room small enough that you can hear me?
Yes.
I want to, I'm sure, be joining with the other speakers in thanking Tom Fort and Carol Meisel's for their leadership and their effort in organizing this symposium, as well as acting as editors for the new volume of collected Kendall Award lectures. It's a very nice, a very collegial thing to have going on. I should say the credit for my being the first speaker goes entirely to my mother, who had the foresight to marry a man whose name began with A. In looking over these statistics, I noticed that the average age of the speakers, the median age, is about 67, but the median age at which the award was received was about 54. That gives you maybe a little bit of perspective. This is just a focusing slide. I thought it would help wake people up in the morning. What I want to do first is to very briefly say something about things that have changed over the past 8 or 10 years. One change, if I get this the right way, I didn't. I'm acquainted with this particular book, and over the past 8 years, or since the 4th edition, I can see at least a lot of changes. Enormous work on thin films, monolayers, Langmuir-Blodgett films, all kinds of things. Enormous work on forces between macroscopic objects, which has led to atomic scale profilometry, atomic force microscopy, and so forth. Beautiful developments in colloid chemistry, and in the area of catalysis, the coming to fruition of the methods of spectroscopy and surface structure on well-defined surfaces as intimately applied to real catalytic systems. Another aspect of history for me is Langmuir. First ACS journal in some 15 years when it was founded in 1985. It's doing well, going from 800 page budget to now some 2,000. It took too much time. I did not want to continue it. Bill Steele is doing a beautiful job as a new editor. And I want to take occasion right now to thank Art Hubbard and Bob Rowell for their magnificent help with the journal as associate editors. But there was a tremendous desire on the part of the surface and colloid community that the journal succeed. The authors contributed, and the reviewers really reviewed. They did a lot of work to improve the quality of the papers as originally submitted. I need to move on because time is short. I want to say something about structure and phases at interfaces, and look very briefly at 3 kinds of interfaces. This is a very recent paper by Nobler and co-workers on fluorescence microscopy of pentadicyllic acid. And what you see at the upper left is a two-phase region, gas and liquid expanded, being compressed. The middle left has become a one-phase region of liquid expanded film. Further compression, another two-phase region, the so-called old intermediate film. And finally, at the lower right, liquid condensed on final compression. Many of you will remember better, perhaps, the pi sigma plot on the right, characteristic plot for a long-chain fatty acid. And at the extreme right of that plot, the two-phase region, single phase, two-phase, way up here, single phase. We can use the Gibbs equation to convert this to an adsorption isotherm. You see the characteristic step increase as one enters that intermediate or middle two-phase region. One can also see phase changes at the gas-solid interface in physical adsorption. There are many examples. I picked this one, a paper by Roquerel, which includes some colorimetric measurements. As you see, argon, boron nitride, and again, an increase here, and the eccentricity and the colorimetric heat of adsorption. As I say, there are many examples, and this was just one of them. Something of interest to us in previous years was physical adsorption of vapors on smooth surfaces measured ellipsometrically. This merely illustrates that P0, the saturation vapor pressure, is a correlating variable, and that the plots of adsorption tend to fall on the same line if P over P0 is used. It's sort of Polanyi potential theory. This system, bulk water, forms a contact angle of about 90 degrees on polyethylene, and hence the adsorption isotherm must cut the P over P0 equal unity point at a finite thickness, so that adsorbed film and bulk water can coexist. So the adsorbed film must have some structural perturbation. It cannot be just like bulk water. The half-shaded points, these are for minus 9 degrees centigrade, and the horizontal half-shaded are for minus 24 degrees centigrade. An indication, at least, that there is something different in the structure of the adsorbed film when one is below the freezing point of bulk water. I had occasion to look over the 1943 collection of symposium papers at the time that Zisman received the Kendall Award. And there's a short paper by N.K. Adam in which he commented that he felt much neglected was the point that there can be surface dissolving, that one does not have an inert and non-interacting surface in adsorption situations. With the great interest in polymer surfaces, this is an example of what might happen, just water nestling into adjacent polymer chains. We have seen this in the case of hydrocarbon adsorption on ice, strong indications of surface clathrate formation. Adsorption of long-chain amines or unsaturated hydrocarbons on polyethylene or on Teflon. On evacuating, the surface is altered. Ellipsometrically, it does not return to the initial optical conditions. So there are, in our experience, N.K. Adam pointed this out many years ago, many indications that the surface of an adsorbent may be altered on physical adsorption. It's hard to see what's going on in a contact angle situation, and I'll show two ways in which some attempt has been made. One was to use a dye-ine. In oriented films and in crystalline dye-ines, ultraviolet irradiation induces a cross-linking, so you get a polymer. And what was done was to suspend a slide of glassy smooth Teflon or polyethylene in the vapor of this dye-ine, then irradiate it with UV light, and then being polymerized, it could be evacuated, it could be coated with a looked at by scanning electron microscopy. So this is what was seen with the 3,5-octadiene on Teflon. Now that Teflon sheet was mirror smooth to the eye. It is not mirror smooth at 10,000 magnification. And those little droplets formed just hanging in the vapor space above the neat liquid, showing about the same contact angle as the bulk liquid does. But certainly that surface has structure. It is not smooth. There's probably an adsorbed film, but that is not thick enough to see. Another type of approach was carried out by Giradella and Frisch and Schonhorn some years ago, taking a glass bead on fernickel metal, chosen because the coefficients of thermal expansion were the same. And then heating the glass bead slowly spread and could be quenched at various stages. And here you see a contact angle situation, but there's a foot. It's not just spreading over the oxidized fernickel metal surface, which again you notice is not a perfectly smooth surface. So there's a lot of structure and complexities in the contact angle situation. What I wanted to emphasize more particularly, though, was some more recent work that we've been doing. This is on adsorption from solution, and has to do with what we're calling irreversible adsorption as a special definition of that term. Namely, the adsorption looks fine. There's no reason to believe any strong chemical bond formation exists. The adsorbed material may be washed off with a good solvent. No indication of any problems, except that if you adsorb some material and then dilute with the same solvent, nothing comes off. Now this was some of the first work done by Mary Zawadsky on adsorption of methylene blue on an anatase. Methylene blue in the older literature is highly touted as a convenient way to make surface area measurements on powders. And we assumed this would be a well-behaved and well-established system. And we're indeed surprised, as indicated here by the open triangles, that on dilution, essentially no desorption. And this means no desorption in days. If the electrolyte concentration, the ionic strength was raised, some desorption. So here is a phenomenon that poses a kind of paradox, because how can one suppose that, let's say, the top isotherm is an equilibrium one, if it's a ratchet, if adsorption can occur but no desorption? How does it know when to stop absorbing? There's a kind of paradox here. The next slide shows a related behavior, similar behavior. This is a surfactant that is much used in the oil industry as an additive, again on titanium dioxide with heptane as the solvent. Again, irreversible adsorption, the open and the dark squares. But notice now that the isotherm depends on the time of equilibration and the degree of irreversibility, or the reversibility, depends on the age. The 40-minute equilibration isotherm showed partial desorption. The 3-minute one took on a somewhat different shape entirely. A phenomenon of retrograde adsorption can be observed. That is, there's adsorption, and then the analytical amount adsorbed from material balance calculations retreats, goes back down, then climbs up again slowly. There are complexities here, kinetic complexities that we found very interesting. The rate of desorption depends on aging. As I said, for 2 or 10-hour equilibration, virtually no desorption. 20 minutes, 120 point, 6 hours, roughly half time. 20 minutes, 4 hours. The 10 marks put in, I think, were for the 3 or 5 minute points. So there's an aging effect here. There has to be some kind of phase change going on. This phenomenon of irreversible adsorption has been known with polymer adsorption. So I want to show one more case. This is Rose Bengal on Titania, showing again the retrograde adsorption effect. This is the amount adsorbed, and you're looking at rapid adsorption and then a decrease in the analytical amount adsorbed, rapid drop in concentration in solution, and then a slow increase. Again, this phenomenon of retrograde adsorption. As I say, this has been observed with polymer adsorption by quite a few laboratories. It's been supposed that there must be at least two adsorbed states, a more rapidly equilibrating one, and then another state which can be reached on aging. It was of interest to see if some sort of kinetic modeling could be made for this. I haven't seen any in the literature, and one would like at least to find a simple model that would reproduce some of the principal features in this matter of irreversible adsorption. These diadsorbents are flat, essentially raft-like molecules. Many of them are known to associate in solution. The degree of association heavily dependent on ionic strength. There's no reason not to suppose that they might also associate in the adsorbed state. So as an attempt at a fairly simple model, what's assumed here is a rapid equilibrium, essentially to give a Langmuir type adsorption, building up to a monolayer. Possibility of bilayer adsorption, essentially PET type, and then some kind of surface association, and on the far lower right, this is just a cartoon to indicate some sort of interacting condensed phase. Nothing specific as to structure is to be implied here. And that last is taken to be slow. This simple kinetics can be integrated. One gets the usual type of algebraic hodgepodge. I should point out that there are, even for this case, 6 variables. A saving grace may be 3 of them are scaling variables or parameters. To scale theta, fraction of surface covered, to actual amount adsorbed per gram. To scale concentration in terms of K1, the equilibrium constant for the first stage adsorption. And to scale time in terms of K-3, the rate constant for the back reaction in the third step. And then the additional adjustable parameters are the ratio of the molecular areas of the associated form, that jumble, whatever it is, to the single molecule, the ratio of equilibrium constants for the second to the first equilibration, and a dimensionless equilibrium constant for the association, the third stage. This can reproduce some of the effects, this kinetic scheme. What's shown here is for the case where, again, in a cartoon fashion, the 4-molecule cluster is occupying the area of 2 monomer units. Theta apparent is the experimental, the analytical amount adsorbed relative to what would be adsorbed if you had a single monolayer covering the surface. Because the first and second stage adsorption is taken to be rapid, the equation starts here, the solution, but practically there would be only by diffusion some dashed line indicating a fast but not infinitely fast adsorption. The amount adsorbed, the apparent amount, is made up of 2 components. One involved in the rapid equilibrium and easily desorbable on dilution, and the other in the cluster or whatever condensed unit is involved and only very slowly desorbed. The time scale is in the dimensionless K-3T units, and since K-3T is the rate constant, K-3 is the rate constant for desorption, only at a value of 0.6 instead of 0.02 or 0.1 would you reach the half time for desorption. So in this case, desorption would indeed be slow, not infinitely slow, but just slow. And one can see here the fraction present as easily desorbable steadily decreases, or conversely, if one starts with the total amount absorbed and then dilutes greatly, there will be a prompt desorption of this component, followed by a very slow residual desorption of the material that's in this condensed form. And then for another set of parameters, assuming some kind of horizontally interacting structure, again, this is just a cartoon to indicate what sigma 4 is referring to. Again, the equation would start here, the solution, but assuming some diffusional but rapid, not infinitely rapid absorption, I've gone into dashed lines. Again, theta apparent, theta fast, the easily desorbable component. And you see this goes through a maximum, and it shows this phenomenon of retrograde absorption. Otherwise, the picture looks very much the same as in the previous slide. So this model at least replicates or can replicate some of the interesting features of irreversible absorption. For this last case, these are the absorption isotherms for infinite time, time 0 and for 0.005 k minus 3t. The dashed line is the rapidly desorbable component, but it shows this business of isotherm crossing. And earlier in the barium dinonyl naphthalene sulfonate case, there was an example of isotherm crossing. So at least we can cover three aspects that make irreversible absorption interesting. The matter of aging, the matter of retrograde absorption, and the matter of isotherm crossing. Well, I've left myself, if I'm correct, about 4 minutes. 3 minutes. So I'll say a word about something that's concerning all of us, I'm sure. It concerns me, the bad repute of chemistry. Chemical spills, chemical toxins, chemical warfare, anything chemical is bad, isn't it? And I'm appalled at the ignorance of the media, the lack of education of the general public. One attempt to tell people that there's really no such thing as zero pollution is a little story which I've entitled Cleopatra's Last Breath. And one imagines Cleopatra, she's clasped the asp to her bosom, and she is dying. So she breathes out maybe a cubic foot of air, to make it simple. That's 1 mole of air, roughly. Now, in the some 2,000 years since Cleopatra, let's suppose this is all mixed up in the atmosphere. And a straightforward calculation will say there's about 10 to the 20th moles of gas in the atmosphere. Most of this is nitrogen, which we can assume has survived since Cleopatra. So her last breath has been mixed 10 to the 20th full, which is a pretty big mixing factor until you bring in Avogadro's number, at which point you decide that the cubic foot of air right here has some 5,000 or 6,000 molecules from Cleopatra. And now my one breath of the 10th cubic foot would have several hundred molecules. Not just Cleopatra, Genghis Khan, Ivan the Terrible, Hitler, Florence Nightingale, probably Margaret Thatcher hasn't mixed into the atmosphere. But the thing is, we're breathing reused molecules. They come from everywhere, and chemicals may be good or bad, but there is no such thing as absolutely pure or uncontaminated materials. You cannot have zero contamination. Even a gallon of gasoline spread throughout the atmosphere would bring more molecules per breath than poor Cleopatra. So thank you very much. Thanks again, Carol and Tom.
the Kendall Award lecturers, the lectures are not open to discussion, but here we are open to discussion. Don't escape. It's 1 minute for questions.
I have a quick question and maybe a comment on the case of the absorption of species from solution rather than the adsorption, where the species diffuse in and are trapped along the way, but trapped reversibly, very strongly bound. It's easy to show because of the extreme nonlinearity that the time for diffusion out can be orders of magnitude larger than the time for diffusion in, because you're emptying traps and the new and the old stuff has to and the same thing could be so on the surface. Basically, that's your kinetics, isn't it? That
It could be, although because it's titanium, to which these data apply, I've assumed that diffusion into the bulk is not
no, on the
important.
surface too. I mean, there's a strong trap
Yes.
on the surface. Something
It's exactly the same idea, I think.
Same
Yes.
idea.
Quite right.
Thank you very much. Our next speaker.